Alrighty, let's get this party started. It looks like my video. Looks like John has disabled my video. Oh well, you'll have to trust me on the ceremonial knocking over the timer that I'll do. So welcome, folks. Welcome. Welcome to Cleveland Big Data on January 2nd, 32nd, 2021, or as the calendar purists call it, February 1st. Welcome. Tonight we've got an evening with Paco Nathan, who's going to talk about scalable machine learning with Project Ray. And as you saw from some of the email blasts, Project Ray came out of the RISELab at Berkeley, which is also the same place that Spark came out of. So if you're not familiar with Paco, I'm really excited to have him here. He's done a great video series on O'Reilly called Just Enough Math. He's written a book, Enterprise Data Workflows with Cascading. He's done a ton of talks at Strata. I look forward to seeing one of those in the future after, post-pandemic. So I'm a big fan, and I've been listening to a lot of Paco's talks in person at conferences, and I'm really fortunate, and we're all really fortunate to have him here tonight. I got to do a few announcements. So again, a Meetup approval reminder. Remember, because to fight spam and the drive-by spams, I do have to approve the Meetup members, just to make sure that they're real people. You still see people try to sneak through with some pretty spammy accounts. So if I'm asking questions when you're joining the Meetup, please don't take it personally. I'm just trying to verify that you're a real person. Secondly, a friend of the show, for the longtime folks know that a friend of the show is a very important and valuable title that is bestowed on people that do a talk at Cleveland Big Data Meetup. And also remember, it does come with some qualifications. You cannot sell that title in the open market. You cannot gift it to your children or to your spouse. It's more like an English peerage. But you are a friend of the show for life, though. Now I'd like to do a recruiting shout out. So for folks that have anything that they're looking for, if you could type it into the chat, and then we can announce them. So if anyone is looking for something, so Chris Barrett from Progressive Insurance, hopefully everybody can see this. Progressive Insurance is looking for several data engineers, and also there's some other positions for data analysts and DevOps engineers. And check out progressive.com careers. So do we have any other recruiting shout outs? I know that Herb from NASA, NASA Glenn, that was interns.nasa.gov. I know he had announced that last week. Also another one, oh, there we go, intern, sorry, I had plural. Intern.nasa.gov for summer interns. Tim Houlihan is also looking for senior data architect at Centric Consulting. So tim.houlihan@centricconsulting.com. He's got his email address right there. Any other recruiting shout outs? Oh, hello, Tom. Tom Callahan, another friend of the show, speaking of, and also Tim, also another friend of the show. Herb is actually a friend of the show too. Reach out. Tom is looking for Elasticsearch engineers, and if you're strong in Java or just like to manage those kind of things, check out elastic.co/careers, or reach out to Tom via LinkedIn. So that's Tom Callahan from Elastic. Any other recruiting shout outs? All right. So there's also if you're still in the, if you still feel like doing some mentoring at a hackathon, I've been mentioning this in the emails. There's a Black Wings Hacks. They're looking for virtual mentors. It's this weekend, I believe, February 5th, 7th. Check out the website. We've got a good agenda for March that's booked. And again, I also will ask for the blockchain challenge. If you think you can explain blockchain to me, let me know. If you've got a deck, I'd like to review it, and then you could be the winner of the blockchain challenge, and we can get you on the agenda for Cleveland Big Data. You guys have seen the posts on that. So without further ado, I'd like to turn it over to, and also thanks also Chris and to the Linux Foundation and ODPI, because they are, Linux Foundation is letting us use their Zoom. So again, thank you very much. Literally, this is not possible without you. Sometimes people say that figuratively. This would literally not be possible without the Zoom from the Linux Foundation. And then they also post the meetups on the Linux Foundation YouTube account, so you can see them later, which is fantastic. And always thank you to the Cleveland Big Data members because you make this possible. So with that, I'd like to turn it over to Paco, and I wish my camera was working because I could do the ceremonial knocking over of the timer. As old timers know, normally we're doing a 3 20-minute sessions. Paco's got the floor, so I will now, you'll have to trust me on this. I'm doing the ceremonial knocking over the timer. It's knocked over, and Paco, take it away.
Thank you very kindly, Doug and John and Chris and Linux Foundation. I really appreciate. I'm personally visualizing the ceremonial knocking over of the timer, just to be in the vibe there. Let me see about sharing screen and hopefully get this going. All righty, can you see a 2D? Yep. URL? Okay, great. So this is the URL for the slides, and I'll post them in the chat, and I'll post them also on the Meetup event landing page in the comments, so that you can have access to slides. One of the things I try to do is err on the side of having slides that are just jam-packed with a lot of links for background material, primary sources, other tutorials, etc. So I've had people, 3 weeks after talk, get a hold of me and say, wow, just finished all the links. So hopefully it's not that bad, but I want to try to get some material shared out there. So hopefully if there's something that's of interest, hopefully there's some links to better material too. Yep, this talk is about Ray, and also, just what's related, what's fitting in there, and some of the practices with Ray, because Ray is actually pretty big ecosystem, if you will. Tonight, we'll look through what's called Ray Core and how we can do distributed systems for machine learning. And we'll also take a look to some extent at RLib, which is for reinforcement learning, which is just one of the verticals on top of Ray that uses those primitives to scale out machine learning. There's other parts of Ray, like Ray Serve, and I can definitely answer questions about some of that. I may have to defer to folks at any scale if I get into some of the edge cases there. But I just want to say that Ray is surprisingly only 3 letters, but already a pretty big word. For introduction, I made the fundamental mistake against all advice to study AI in grad school back in the early to mid 80s. And, everybody told me, or at least the people who were my elders, so to speak, in computer science, were telling me that it was a real waste of time. And then I made an even more fundamental mistake. I was at IBM Research as a grad student, and my lab partner, who she later became a relatively well-known neurophysiologist, I won't embarrass her, but we spent a lot of time in a little cube, and she would not stop talking about neural networks. And so eventually I was like, Janet, I promise I will study neural networks. And I ended up doing about 7 years of research and development in neural networks. So I'm very grateful to her for that. It was kind of an odd time because it was well before we had enough compute power. So AI winter and all, I went off to places like Bell Labs and whatnot. And I did a lot of network engineering and did some network security and did, some database along with that. Somewhere around 2005, 2006, I had these really strange calls out of Seattle. They wanted to throw a hypothetical at me and say, how would I use a thing that didn't exist? And then they showed me a website and asked me to sign up. So I ended up being one of the really early guinea pigs for AWS, and eventually ended up on their advisory board. I got to do some early 100% cloud architectures. Uh, anyway, long story short, one of these ended up being like the first real large headache instance on EC2, because we actually, the Jira ticket was there that was preventing Hadoop from running efficiently on EC2 because of some IO problems. So our team like got in a guy to help us with that, and we fixed that ticket and pushed the commit. And the gentleman was a young programmer named Tom White, who later wrote the book Hadoop: The Definitive Guide. And that became a case study for EMR. And then from there, I got involved with Apache Spark and got to meet a lot of folks, maybe some folks here through, a lot of what was going on in the Spark community and related machine learning since then. So just as like, reminisce, but also a proof point here. This is the documentation for what was called the association engine. It was neural network accelerator hardware. We began this in 1989. I got to work side by side with a gentleman who's unfortunately departed, Mike Gallup, who had been the lead circuit designer for the 68040. If you remember back in the dark ages when Motorola had these huge chips that went into Macintosh and Linux and whatnot. Mike had just come off the 040 project, and he and I basically was writing microcode to translate neural network algorithms into the hardware that he was simulating in Verilog and whatnot. And really fun. I know it says Motorola confidential propriety. There's no laws being broken here. There was a patent filing for this. So actually that stuff's all public now. But again, we knew we didn't have the compute power back then. We were trying to get it. I ended up doing some work for DoD along these lines. They were really interested in pattern matching. And one thing led to another. Okay, so roll the clock out another, 20 years? And I had been involved with AWS for a few years, and I got summoned to testify at Berkeley. A gentleman named Dave Patterson, who was one of my heroes when I was a student. You might know David. He created something called RISC, also something called RAID. He had written a paper trying to define cloud. What does cloud computing mean? Because this was still pretty early days. And somebody invited me to critique the paper, which, I'd just come off of a large project in industry using cloud, and, we'd seen some downsides, and the stuff in the paper didn't really kind of fit with what we were seeing in industry. So I was pretty frank, and I found out that that's maybe not the best approach with a famous professor, because there's actually a video of David grilling me for about an hour in front of a bunch of grad students. And fortunately, one of those grad students was named Matej Zaria, and he was a couple years out, well, 1 year away from starting a new project called Spark, and got to work with Matej and others. And as Doug mentioned, I did a book, a video series. It started as a book, but it became a video series and also a collection of notebooks, trying to teach IT executives about advanced math so that they could understand what was going on with big data. That was the idea. And it actually worked. We tried to, step back and make sure that the managers in the room could get some hands-on with some code. And, even if they hadn't taken 3 years of calculus, they could see what was really going on, learn it from almost like a business school perspective about math applied to data. And that's actually some of what I'll show here tonight. And so, that was 7 years ago now. So there's a new project. It's actually Just Enough Math Volume 2, and it's tentatively being called Graph-Based Data Science. And I'm working with my friends over at Manning Publications on that. So we hope to get that out later this year. Hopefully there'll be some stuff out before long. We're actually doing a conference called Graph Data Science in 2 weeks, which I guess is January 45th. All right, so connections. I really love history of science and history of engineering. And I don't know if anybody out there has ever met James Burke, or if you're fans of his shows, Tomorrow's World and Connections and all those. I'm a big fan. I got to meet James Burke a couple of times. 30 years ago, passed him in an airport, and my friend reached out and we had a chat. And then later, he's given a few keynote talks for O'Reilly conferences. And backstage, I got to have a really long conversation with him right after his keynote. We kind of talked shop. For what it's worth, I actually ran network operations for one of those shows. One episode in '98, it was a real-time live televised Turing test. And it was the Tomorrow World franchise. It was long after James Burke left, but kind of fun. So connections. Let's talk about what's going on with Ray. And I want to back up and look at really what was going on ever since Hadoop and Spark, and kind of the trajectory of what's led into where we are now with big data leading into machine learning. So Apache Hadoop, this famously implemented Google's MapReduce. But that calls back to something called lambda calculus. If you ever want, there's the original paper is linked here from Alonzo Church back in the 40s, and then there was a review of it that's actually a lot more readable. But the primary sources are linked there. There was this notion of operators on data. And there's kind of a design pattern that came out of it called map filter reduce, which if you've done work inside of SQL engines, relational database systems, this is the kind of design pattern that gets applied over and over. And that's a lot of what led toward what we were doing back in the day with Hadoop. I was on a team where, like I mentioned, we were working with AWS very early on, starting with, we had launched the company in June of 2006, and AWS went out in August 2006. And I already had a little bit of a preview. So I went to the VCs and said, hey, let's go all in on the cloud. And they learned about it and came back and said, yeah, we're down with that. So we actually got to build out a new tech startup on AWS right when it launched. And a couple months into it, we ran into some bottlenecks with our workflows. We were doing machine learning. We were doing a lot of natural language. And one of the young engineers suggested a new open source project that had just been launched. This was December 2006. So this new project was called Hadoop. So we gleefully adopted this and tried to make sense of it. It was very early days, and there was a lot of rough patches, but one thing led to another. And so Apache Spark, roll the clock out another 3 or 4 years. Matei had done work at Cloudera, and I believe he'd been involved with Google, but he'd definitely seen a lot of industry use cases on his way into grad school. And so Apache Spark was really trying to leverage a lot of limitations that we'd seen in Hadoop. And the other thing that was going on is Apache Spark really at its core made a lot of use out of functional programming constructs, closures, some other parts too, but how can we use functional programming to represent formally some of the goodness that was going on back in lambda calculus, and then translate that into engineering in distributed systems, particularly using actor pattern and others. The idea was to build out what's formally called an applicative system for data analytics workflows. So I tried to go into this in some detail in the Enterprise Data Workflows book a decade ago. But truth be told, I think Matei spelled it out brilliantly in this paper here where they introduced Spark. Spark had originally come out of another project that I'd been working on called Mesos. And this is the paper where part of the Mesos team introduced Spark. It has been cited many, many, many times. I definitely recommend reading it, just kind of as a flashback to the past of what were they thinking about. But it introduced some really novel terms here. So they really came out and said, hey, we're going to put a stake in the ground. We are a cluster computing framework. And they were really informed by what Berkeley had learned about cloud, what David Patterson had led to study formally what was going on with cloud. And they were implementing notions of distributed shared memory. And also importantly, they were implementing notions of lineage so that, if you have a bunch of data and you think of it as a working set view of that data, you have it in different partitions. If you lose a node in your cluster, can you use the lineage to reconstruct the lost nodes efficiently? Because if you can, there's some other mathematical tricks you can get away with to really optimize it. So this is the thinking that went into resilient distributed data sets, RDDs. And I think these days it's in Spark, people don't really even talk much about RDDs. It's more data frames and above. But this is really the fundamental layer underneath. So if you've never looked at this original paper, I definitely recommend it. I think there's a lot of really amazing forward thinking back then. And in particular, I mean, I've been around database management for a long time. And I wrote a book a couple of years ago, a mini book that's called 50 Years of Data Management. Just trying to compare what's happened decade by decade, because there's some really great stuff back there going, even back to like IMS in the 60s. And I'm definitely showing my age because I actually have written COBOL on IMS. Spark made a difference. And what they did was, whereas SQL was about declaring workflows implicitly through a language, and then having this kind of black box, highly optimized SQL engines underneath optimize things, you can see the query plans and you have a little bit of way to adjust that, but realistically, it's a black box. Spark instead took a much more open approach and said, instead of declaring a workflow, we're going to describe the workflow explicitly through this API that leverages some things out of functional programming. And we're going to make it available inside of Java, inside of Python, inside of R, et cetera. And, they really introduced a lot of cross-stack ideas that these days are coming out more in things like Project Arrow. But the idea was to really optimize programmatically and have it all in open source. And by opening that up, they really addressed a much broader range of possible integrations. And over time, that's proven to be very robust. Now, my friends who are in investment banking, of course, they immediately point towards Snowflake and say, no, it's all SQL. But I actually think that this open approach and integration in particular is the hard problem that we face in enterprise when we're working with data workflows. So that openness was a really interesting way of bucking the trend, really. And that had started back with Hadoop. But there's something here that I think really needs to be understood to see where we're at now. So a little bit of a rear view mirror reflection here, but I think it's really important. The mainstream success of Spark couldn't have happened except for some things that were introduced in the mid 2000s. I mean, Scala language itself was 2004, and PennyMD came out 2005. So commodity multi-core processors really didn't start till then. Cloud computing, AWS was introduced mid 2006, and actor model in Scala came out in 2006. And with all of these were things that the thinking for Spark was dependent on. So I really want to kind of peel it back and point to, gosh, there's some strange things going on in sort of where like advanced math meets programming language, and what implications does that have on distributed systems? And, for that matter, the hardware is just changing really rapidly under our feet. And so a lot of that is really the fundamental formula for like what went into making Spark happen. I tried to dig into this years ago. There was a keynote at Big Data Spain, and if you want to look back, it's pretty crazy, because when they asked me to make like predictions, it was like late in the year in 2014, and they wanted me to come out and like make big predictions at their conference, and it was pretty crazy because I'd been teaching at KTH University up in Stockholm just before, and I'd unfortunately gotten really sick up in Sweden. And I had a couple days where I could just like hole up in the hotel and try to recover. So I landed in Spain to walk out on stage for this talk, and my voice was gone, totally gone. So, I get out there and I'm like, hello, my name is Paco, and I'm here to talk about big data. And the Spaniards were like, awesome, that's just exactly what they wanted. So it's pretty crazy. I've gone back to what's now called Big Things, but Big Data Spain every year, and I highly recommend it. It's one of at this point, it is the largest big data, machine learning, AI, data science conference in Europe. But anyway, there's some pretty crazy views of what was going on 7 years ago. Well, I guess what, 6 years ago. And, where do we think this was headed? And so it actually came out pretty close. So I want to peel back and talk about something that's underneath here. If you haven't seen it before, this is not talked about a whole lot, but I think it's really important. So there's a question, like 7, 8 years ago, 8 years ago, there was a question on Stack Exchange. And it was, what use are groups, monoids, and rings in database computation? And the word ring or group or field or semigroups, all that, monoids, that comes out of abstract algebra. So if you did have the choice experience of going through graduate level mathematics courses in university, you might have had to handle a lot of modern algebra, category theory. I had a rather traumatic first time through that, but later on it sunk in. But the thing was that back in 2013, actually in 2012, this was going on at Twitter. And so there's a couple of talks here that are linked, but it's about this project called Algebird, which, if you've never heard of it, I definitely recommend taking a look. As far as big data, this thing was foundational, but people don't talk about it enough. So I'm going to try to play James Burke here and peel back the layers and show what were the fundamental things that changed. When LinkedIn launched, the CEO was a close friend of one of my close friends back from grad school, and he had managed to pull in a whole bunch of funding. And when it came to the data centers at LinkedIn, they had more money than they knew what to do with. So they had a lot of budget, they bought expensive equipment. And when LinkedIn built open source, it sort of presupposed that you had a pretty healthy IT budget. And this was actually a problem early on, even going into days of Kafka, but definitely, some of the earlier LinkedIn projects for big data, they were very much tilted toward, you've got some expensive hardware. And of course, when Facebook, another social media, big data test case tech company, when they were building out their data science group, of course, they had all kinds of money too. When Twitter came along, they didn't really have the money. They were much more scrappy. And so instead, what they did when they were building out their data analytics at scale, they went and hired up this team where it's math professors who had gotten into novel ways of managing data. And so they brought in a couple of people, Oscar Boynton and Avi Bryant, and well, there's a whole crew there. But they really had more of the math professor view of the world. And they knew how to use abstract algebra to cut the workloads on data analytics at scale down by a couple of orders of magnitude. So for Twitter, this actually meant, translated into millions of dollars. And Algebird really set the tone. If you, like I said, a book that I did years ago was called Enterprise Data Workflows with Cascading. Cascading had a couple of variants. One of the chapters there is about something called scalding, and Algebird is based on scalding. And two of the principles, there's some really fantastic talks here. One is called Add All the Things, that was at Strange Loop in St. Louis, 2013 by Avi Bryant, really nice guy. And Oscar Boynton, who did algebra for analytics at Strata the year later. Some of these ideas made their way into Spark. And in fact, I'll probably get in trouble by disclosing this, but I was actually in the room where Oscar came in and talked with Cascading about, hey, we're looking at Spark. We're thinking about moving over to Spark. We'd like to get the following features into Cascading. And unfortunately, that meeting didn't go well with the person leading the company. Kind of humorous, but anyway, some of these ideas eventually percolated out and made their way into Spark. And I wish that more had, because I think that these folks were really onto something brilliant. And you can definitely adopt libraries for some of this, but I haven't seen it go quite mainstream enough. And there's a point to this because we're kind of leading up to some of the sort of evolutionary soup for Ray. but I just want to say that there are these Scala-ish kind of notions about big data that really informed Algebird and Spark, Kafka, Akka, a lot of things. And I mean, we can talk about that regardless of the programming language, this kind of bridge between functional programming and what we can do with managing and really leveraging distributed systems at scale in light of how hardware has been evolving so much. That's the real quintessential point. It's really those three pillars. And so I want to transition here into going back into, I talked before about Berkeley trying to have some very deliberate and formal definitions for cloud. And we've gotten things like Spark and Ray that have come out of that, and Mesos also. So my former boss, Jan Stoica, along with his colleague, Dave Patterson, they led this work on a paper in 2009 that was called Above the Clouds. And that was the one that I sort of got suckered into critiquing. A really fantastic paper because it's been cited 17,000 times, more than that. They went through David Patterson's methodology in engineering of trying to understand a new thing that's emerging, mostly by going out into industry and like interviewing gobs of people and going through a methodology of how to put the results of those interviews back together. But they came out with some definitions that were truly prescient, and they sort of spelled out where was cloud going, at least for the next 5 years, but really for the next decade. Let's see, here's the paper. It's called Evolution. It's called Above the Clouds: A Berkeley View of Cloud Computing, and it's a really great read. If you've been around Spark, you might recognize some of the people on that. Definitely some of my former colleagues and friends. Well, former colleagues, current friends. But Mike Armbrust, definitely Anthony Joseph and Andy Konwinski, Matei, Jan, etc. A lot of the crew that started Databricks. Now, one thing about this paper that was really, really interesting is that early on, Amazon, by the way, Amazon had been part of what helped inform this paper. They'd talked a lot with Amazon and Google and Microsoft and others. Amazon realized pretty early on that they were going to have to take their internal practices of what they were doing with cloud and effectively kind of make them dumbed down. They were going to have to make something that was recognizable for what was held to be more of like an industry standard. I mean, at the time, everybody and their brother was using VMware. So to make cloud offerings more recognizable to IT staff, they tried to tilt things and make it look more and more like VMware. And I can tell you from early days in AWS that there are a couple of notable instances where Amazon tried to take actual production systems that they were using inside Amazon and present them to the rest of the world and say, hey, would you like to use this? And it was just, people would bug eye and go, I have no idea why you would use that. So it took a while for industry to sort of catch up to what Amazon has sort of involved internally. But anyway, this paper kind of goes through it. Now, what's interesting is that this was done in February 10th, January 43rd of 2009. 10 years to the day later, David Patterson and crew, and Jan, they published another paper as a follow-up, 10 years of the day. And this was led by a gentleman named Eric Jonas. He's now a professor at U Chicago. If you get a chance to ever catch him, please do. He's a treasure. Eric, I got a chance to have dinner with him one time, sat next to him one night at a dinner accidentally, and we just hit it off. But Eric is the kind of person who was such a nerdy teenager that he wrote his own AWS simulators as a teenager, just because he loved cloud so much. And so he eventually ends up being a postdoc at Berkeley in the lab that created Spark. And while Eric was there, he noticed, he started asking people, he's like, it's kind of weird, but like, less than half the people here, the grad students, have ever even run a Spark job. And this is the lab that created it. And then he started looking at the machine learning students, and it was like low double-digit percentage. I think it was actually single-digit percentage points of how many of the machine learning students in that lab had ever even used Spark. And so Eric was like, okay, this isn't right. And he wanted to figure out why. And so he started asking them, and you know what it came down to was a lot of the genesis of this paper. So Eric really kind of, he does something really interesting here where he looks at both the physics that's involved of what's driving cloud, what's driving a lot of the IT infrastructure that's being exposed through cloud, and the fundamental components that Intel and others are providing, uh, network, disk, processors, memory, etc. But then he also, another layer up above that, he's looking at the economics of what's shaping it. And a lot of the takeaway is that, 10 years later, the notion of cloud has shifted fundamentally, and the services are moving up the stack. The upside is you're not getting something that's presented as VMware anymore. You're getting much more high level services that are probably closer to your use cases. On the other side, there's the danger of data gravity and like vendor lock-in and all these kind of things. So this paper really tries to peel that apart, and it's a really good one. It's a great read. But the key point here was this decoupling of computation and storage. And so the message that Eric has coming out of this, and I mean, this is what we talked about at dinner, the message that Eric has on this paper is that initially there was a big disconnect. There's a big distance, if you will, between the storage grids like S3, their performance envelope, and what was going on inside of a VM in its memory, the processes that you're running for your use case. The performance envelopes on those were just really pretty far apart. So if you wanted to have a robust system, you needed to have layers of frameworks that were going to intermediate. Otherwise, there were going to be failures. So basically, there were a lot of kind of data frameworks that evolved because the memory space wasn't big enough, because S3 wasn't fast enough, and things evolved to go in the middle to fill in those gaps. And it's sort of the old story. I don't know if this is from Don Knuth or Dijkstra or whom, but so much of computer science is just about layers and layers of caching. And that was very true about the evolution of cloud. But what Jonas is pointing out is that now we're seeing a decoupling of computation and storage where they scale separately, they're priced independently, and the storage has just gotten faster and faster and faster and more capable. And really, I mean, S3 is the success story of AWS. People think about more of EC2 and all, and they've done great things, but S3 is just phenomenal where they've come from, what they've been able to pull off. So what this points toward is basically a dismantling of the layers in between storage grid and memory. And so this is where, again, this same team that had kind of like had a crystal ball and could look 5-10 years ahead in cloud back in 2009, they did their follow-up 10 years of the day, and they're saying, okay, what we're seeing is this abstraction of executing a piece of code instead of allocating resources on which to execute the code. And that's a lot of where they're going when they talk about serverless and about the economics of what's rolling out, and also just about, a lot of deprecation of many, many layers in between grid and memory. And that's important because remember that what Spark was talking about was having this kind of distributed shared memory and having a framework for that cluster because the different nodes in the cluster were probably going to go away. And so some of the fundamental assumptions for Spark have changed over the years as the cloud offerings have evolved. And especially, pay for the code execution instead of pay for the resources. And that's a very big change in the economics of cloud use at scale. And it's true, we might be talking about AWS, but this is true about multi-cloud, it's true about hybrid cloud, et cetera. And so, Berkeley is kind of tilted their thinking away from frameworks more toward libraries. And in the open source projects that I'm involved with, I'm seeing this also. More and more, you want a library that will fit in with your use case as opposed to having to fit your use case into somebody's framework. And I think that's just going to continue to snowball. And, the vendors are going to push this. There's a lot of business implications. I think it has a lot of bearing on data engineering. And I don't want to get in trouble, but I'm working on a project with some colleagues over at NVIDIA. And we're actually doing a little mini book about this topic, just like some of the changes that fast evolving hardware and the workloads that we need for machine learning, what kind of changes does that have on data engineering? And actually, it's a really good message. There's a lot of great changes it has for data engineering, but brace yourselves. So that's going to be our Q1, Q3, or Q2 project. So these two papers from Berkeley, I think, are really foundational. And it doesn't diminish data engineering. It's just that the field is going to undergo a lot of change. And I think that it's significant. I think it's sort of like that whole arc from that I witnessed from like mainframes to Linux VMs. It's very different. And part of that is what I'd point to. This is kind of a crazy, evil, mad scientist thing to say, but hardware is moving faster than software. Software is moving faster than process. And 20 years ago, it was different. We've been taught in software engineering that process is something very general. Agile applies to a lot of different kind of projects. Software is something that's very abstracted. And then hardware is something way, way down a low level. You probably don't ever interact with the hardware directly. It just gets faster, cheaper, better, right? But that all changed. And a lot of it is because of these things that we saw, like deconstructing Spark leading toward Ray, talking about, commodity hardware servicing log file needs, but then it gets a little more sophisticated using actor pattern because we introduce more of the machine learning. And then, a few years later, we get into deep learning requirements, which change it all around. So long story short, we're seeing that the workloads that we have today, they really require something different than what Google was doing in 2005 with log files. We're talking more about complex networks, graphs, DAGs, if you will. And within those, the workflows that lead toward machine learning models, but we're also talking about, where they have accountability, where they must incorporate the human side of it with domain knowledge and, transparency and a lot of the human in the loop kind of aspects too, both for making it better, but also, compliance and things like that. So the hardware is really one of the things that's like turning this all on its head, a lot of the assumptions. And if you haven't seen it, I'll as evidence entered into the court, I'll point toward this paper. This was done at the Bay Area ACM meetup in 2013. Jeff Dean gets up and starts talking about the need to train neural networks at scale. And I think a lot of people are like, what? Huh? But he starts talking about this thing called deep learning and how they have new data centers and they have, really different kinds of architecture. They're not going to do this with MapReduce. They're really looking at how some of the fundamentals of like switch fabric and all that inside their data center are changing how they have to look at software. And they really have to like optimize for training networks. And it's pretty crazy because, he's basically spelling out what just a couple of years later would be introduced as TensorFlow. And roughly around this time, a friend of mine invited me to lunch, and then his whole company got snarked into Google a couple of weeks later, and he later ended up leading a little project that ended up being part of it being called TensorFlow. So here's kind of a preview. It's this great video called Taming Latency that Jeff Dean presented, and it really drove home a lot of the point of where Ray is at. So what I would characterize is like, if you go back to the 1990s, if we were all in the same place and eating pizza and beer, I would ask, how many people out there ever had the privilege of writing MPI code? Because I certainly did. And I used it to pay the bills at one point. And boy, that stuff is bad. But if you go back to the 90s, the idea of like parallelism, there's some stuff that's like pretty ad hoc and pretty squirrely at the end of the day. And there's, for me, it's like synonymous with tech debt. And I've actually had to go back in and recover some systems and their tech debt in MPI. Anyway, we get into the 2000s and Google followed with Hadoop. They start talking about these distributed systems that work in phases. So you have a map and a reduced phase, and you're doing your filtering, you're doing aggregation, but it's kind of like lockstep in phases. And the typical problem there, like what Twitter encountered, was you can be doing a really large MapReduce job that requires so much of your cluster, but then you get down to this one little point in your network where it's like your utilization rate for your cluster drops to almost zero because there's some asymmetric, there's some node that's a bottleneck. And, with Twitter, the thing was that, back in the day, most people only had 205 followers on average on Twitter. And so you chunk along all those processes. And then you get to Lady Gaga, who has like 13 million followers. So you get these real skews in the data distribution per node. And it causes this sort of phase lock approach to lead to some really serious inefficiencies where you're just burning up carbon on that cluster, but not doing much of anything, waiting for one tiny little node to finish. So what Jeff Dean is talking about was rolling the clock out to the 2010s, where they were recognizing a need for having more point-to-point, peer-to-peer network sort of thinking, if you will, within a more contemporary kind of data center. Really fast switch fabrics, large memory spaces, a lot of multiprocessors. The thinking that went toward TensorFlow and other things subsequently like it. And so you see this echoed in the projects at the time. Obviously, MPI back in the 90s, Hadoop and Spark in the 2000s, and leading in the 2010s. And then currently where we're at with ideas of like PyTorch, TensorFlow, Ray, which are much more about graphs. And the graph part of it, the network part of it is really telling. So in going back to, I mentioned about a small book called 50 Years of Data Management. The graphs have almost always been there in data management. It's just they've been buried. And the trick ever since John Tukey and others back in like 1961, the trick about early notions of empirical data analytics were that if we have a complex graph, which we do when we're doing SQL joins or anything like that, if we have a complex graph, well, we can just sort of shove it into a matrix. I mean, formally speaking, it's a tensor, a complex graph, but we can do some tricks. We can cut some corners, and we can take our graphs and shove them into a transition matrix or, well, anyway, there's a lot of different formats for this, but you get your stuff into a matrix, you can apply linear algebra, you can do factorization, decomposition, and most of the libraries that do any kind of intense data analytics, they do this. And in fact, a lot of them have been written by the same person who's now a professor at Texas A&M. So this notion for the past 60 years was, yeah, you've got a complex graph, you've got a lot of metadata, you need to be able to understand it, but to make it work, we're just going to shove it into a matrix and do some numerical libraries. However, we're finding that there are reasons for wanting instead to use more sophisticated patterns like actor pattern and things that lead toward more explicit distributed systems, being able to apply things like class hierarchies with category and inference, the kind of stuff that Twitter was doing with algebra, that some of the stuff that went into Spark, because these days we actually are pretty interested in things like inference and uncertainty measures and causality, because oddly enough, we use this machine learning, and in some cases, auditors come knocking and they want to know answers to hard questions. And if everything has been, the corners are cut and you shoved it into a matrix and you did number crunching, there's no way you're going to be able to back out those questions for the auditors. So we really need to be in a world of working with machine learning where we can reach in and explain why was this particular component doing this particular thing. And I like to point to a gentleman who 40 years ago, I was probably almost to the day, well, no, actually 39 years ago to the day, I would have been fighting over the laser printer with him. Don Knuth and I both used to hang out in Margaret Jack's Hall at Stanford in the early to mid 80s, back when there were only 2 laser printers on the entire campus. And he was working on latex and I was working on something else, and we would fight over the printer. Don is really an amazing, amazing person. And of course, there's a famous quote that says, the real problem with programmers spend too much time worrying about efficiency in the wrong place, and premature optimization is the root of all evil. And I think that that's been the story of sort of premature optimization on what's the real context when you're working with big data, when you're working with machine learning workflows. And fortunately, there are people who are a lot smarter than me who are going after this hardcore. Joe Hellerstein at Berkeley at RISELab has been working on data context, and he has a lot more eloquent ways to put it. So, Record. Let's talk about this. Let's transition. So we had these ideas of like hardware evolving very rapidly and different kinds of workloads. This idea of workflows and needing to work with integration with a lot of different components. We have this idea of how much hardware is changing and then how we can leverage some aspects of functional programming and abstract algebra and all to really make sense out of the distributed systems and then deliver things that are much more efficient at scale. And the current thinking on this, coming out of what Eric Jonas and others had analyzed about the team the lab at Berkeley that created Spark, and looking at the cloud offerings these days, the answer has been embodied by this Ray project. And even though it's relatively young, they've really picked up a lot of speed, working to make PyTorch and TensorFlow and others faster. I don't know if you saw the news today, but Spacey 3.0, shout out to Inez and Matthew and friends over there at Explosion. They did their 3.0 release today, which is now based on Ray and making use of a lot of Hugging Face. So there are deep learning transformer models throughout the workflows inside Spacey. Similarly, a lot of integration with Dask and with Selden and weights and biases and others. So Ray has, in a short amount of time, built out a really phenomenal ecosystem. Here's a talk by Robert Nishihara, who's the CTO and co-founder of Ray. And I'm grateful to get to work with Robert. And it's a really great overview from Ray Summit of just where they're at. To break it down, looking at the core parts of Ray, there's really a kind of pattern language. And there is a graduate course at Berkeley right now, or has been, about a kind of pattern language for distributed systems. And so the idea is, again, not to build a framework, but to focus on building libraries and integrating with other libraries. And how can we take a lot of what we've learned over the years from big data and be able to go back and revisit some of the older, cruftier libraries that we like and start to parallelize them in a much smarter way. And so I'll break this down with some code examples here, but there's a handful of major patterns that we're working with in Ray: test parallel, parallel iterators, joblet, etc. And these have a lot of impact on the kinds of workloads that we use throughout machine learning. And also on a lot of popular packages out there that they can plug right into. The idea is to mix and match these based on the use case. And it's not a tight coupling to any particular framework. Frankly, I've worked on projects where I could go into some existing body of code and use about 4 lines of Python and parallelize it with Ray. So it really is like, let's revisit what's out there and just make it faster, make it work in multi-cloud and hybrid cloud much more effectively. And a lot of the magic for this comes down to, taking some of what was learned out of Spark and sort of pushing the ball a little bit further down the field. So, Ray is using closures, but then also using decorators to kind of generalize beyond the patterns that were used in Spark. And I mean, if you look at PEP 318 and others, you can kind of see how this works out. There's an article that I linked here about closures and decorators in Python. And a lot of this really boils down to how they're making use of async IO, and realistically that in the decades since Spark first came out, basically Java and Python have both come up to speed to have a lot more primitives to support functional programming. And so, Ray is trying to take advantage of those directly. So one of the first and most general patterns is test parallel. And this is fundamentally what's going on inside of Hadoop and a lot of what's going on inside of Spark. The idea is that you have a function and you add a decorator to it to take advantage of running it through async IO across a cluster. So really just write a function in Python or and then you do this ray.remote decorator. And there's a similar kind of approach in Java, but I'm not going to go into Java too much today. But this depends on sort of Hadoop notions of parallelization, where you have strong guarantees about data independence and their statelessness. The sort of data recovery notions that we had back in Hadoop are being used in the task parallel pattern. And there's something related called task graph, where you look at task parallel patterns that are organized in a DAG. If I want to go back in the day, I think probably one of the good references for this, you want to dig into some of the early thoughts about it, Patterns for Parallel Programming from Mattson et al. From 2004 is probably a pretty good reference for that. And just to do this, again, it's like define a function and then add a decorator. And then when you go to call the function, instead of calling it directly, you have this pattern where you say call the function dot remote. That gives you a handle, an object reference. And then later at some point in time, you're going to go back and collect the values for those object references. And so by that mechanism, then these different tasks basically are your serverless tasks that just run out somewhere on your cluster. And you can get a little fancier. You can use a with clause so that you can actually spread these across different multi-cloud environments and be able to parameterize those more deliberately. Like you might have GPU credits running on Azure, but then you've got some other servers that you have long-term that your team has running on AWS, and some of the stuff you just want to do on your laptop. And you can have like one short Python program with a few decorators and a few with clauses, and boom, you run it across 2 clouds in your laptop. And I seriously, I had a big project that I was doing for NYU and USDA, a bunch of ingest of natural language, working with a bunch of crufty PDF files. And we walked in and with 5 lines of Python parallelized the whole thing. And I've heard this story over and over. So just with task parallel, it's really powerful. If you want some tutorials about that, I can show some stuff later on hands-on, but I mean, this code, what I showed back here, that's pretty much it. There are some tutorials you can run on Colab. There's also the Anyscale Academy resources, and here's the Ray tasks. If you find any problems on the latter one, the Anyscale Academy, I'm helping you go through right now. I have some PRs to catch up, but this tutorial should work pretty well. I tested out the Colab, definitely. And we'll be adding more too, but task parallel, this pretty much covers it. The next one, other pattern, is remote objects. And this is about having a distributed object store. Think of a key value store. And this is sort of an evolution of the notion of distributed shared memory that Spark had. So it's roughly a lot like parts of Redis. The idea is that you define a key and an object, and the object goes out and lives somewhere in the cluster. So it's a lot like distributed Redis, but you have the key to it, so you can grab it anytime. One caveat being that these objects are immutable. So once you create them, that's what they are. But this really gets back to some of the more theoretical notions of shared memory. So I've got the Wikipedia page that has a pretty good description of shared memory. And for this, it's, again, key value. You've got Ray that can put an object out there. You get an object ref back. And then at some point, you dereference, you evaluate that object reference and get the value whenever you need it. So puts and gets. And here's just a short little program to show how that can be useful. But if you've done any work with key value stores, you know this pattern already. The thing is, now you can just mix and match this with other code with just a few lines of Python or a few lines of Java. A lot of the meat, a lot of the real beef here, or what's going on, is actor pattern. And I gotta admit, I had to read actor pattern several times before it made sense. And then I forgot it and had to go back and reread it. And I mean, over the past decade, I think I've probably read about actor pattern, 7 or 8 times. This makes it a lot simpler. The idea is you create a class and you have this Ray remote decorator for the class. And so now, instead of having data independence and statelessness like you would with task parallel, now you have stateful message passing semantics just by operating on a class instead of a method. And if you really go back, Carl Hewitt et al., they this paper from Ichkai in 73 is really the one that introduced this notion. But the idea is you've got some sort of stateful message passing amongst actors. Got a nice UML diagram for it, that live somewhere out on the cluster. And so real simply, just to do an actor pattern, we've got a real simple class for a counter. And so there's an init and an increment. And then we put the decorator on it. And then when we call it, we say counter.remote. That gives us a handle. And then whenever we want to pass a message, we dereference that. So then we call one of the methods, which would be like remote. And we can dereference that and get the value back. So very straightforward to use. I remember the first time that I saw actor pattern in Java, and it was definitely not this simple. But there's some good tutorials, again, on Colab and inside of Anyscale Academy. And Dean Wampler, you may have run across my colleague and friend Dean Wampler, and hopefully soon to be co-author. Dean did a really phenomenal implementation of Conway's Game of Life using actor pattern, which is it introduces some dimensions of Conway's Game of Life that I'd never seen before, particularly using colors. Anyway, cool stuff, but it's on the Anyscale Academy Git repo. Okay, so another pattern is called parallel iterators. And so this is basically it's an API for being able to do data ingest and processing, a lot of the ETL kind of stuff, but in parallel. And the interesting thing is that the iterators are fully serializable, and they can operate over infinite sequences of items. And so that way you can serialize them and send them out somewhere on the cluster so that some actor can work on them inside of some task parallel, some collection of task parallel tasks. So kind of a serverless view of infinite iterators, if you will. But these get passed out to the remote tasks and the actors, and they effectively handle the sharding, if you will. And so you get these transformations based on method chaining, kind of like what you saw in the early days of Spark with RDDs. So there's some notions that carry over there. And here's a tutorial for it. There's a IPython notebook in the Anyscale Academy. And just to show an example, real straightforward, but here we've got, again, our friend the decorator. One difference being that here we're showing running Ray init. But yeah, then we've got an iterator up to, I've got my glasses on, but that looks like 1 million, but we're gonna shard it into 4 partitions. And then we can send it out across the cluster. Just, you see there in Python, that's a list comprehension, but it runs across these different shards across different remote workers. And gosh, when I was at InView a decade ago, our sharding with MySQL was a lot more complicated than that. So this is making the programming a lot more straightforward. There's another pattern that's called multiprocessing pool. And this is where you can leverage on top of actors to use a pattern that's relatively common in Python programs that are already distributed, but now you can make them scale out to a much larger extent. So this is a drop-in replacement for the multiprocessing.pool object that you'll see in Python. And it's really straightforward. I mean, it just really is a drop-in replacement. Here's a brief tutorial about it, but if you've ever had to use pools and queues in Python before, this is going to look very familiar. And then another pattern is called joblib. And so the backend that's used to parallelize scikit-learn, machine learning workflows with scikit-learn, that's joblib. And there's other places that are using joblib as well. It's also part of the same tutorial as the multiprocessing pool. But this one is super useful because I don't know about you, but when I'm building machine learning workflows, I use scikit-learn a lot. And even for more advanced stuff, if I get into using Lale for AutoML, under the hood, it's scikit-learn. I'm doing a lot of work on graph ML these days, and we use a lot of scikit-learn. So definitely, I think that this is, again, underscoring this idea that you can go into very popular projects like Pandas, Scikit-learn, Dask, PyTorch, etc., and do some things under the hood with just a few lines of code and be able to run it across multi-cloud clusters. That's what's going on with Ray. And so just to show inside of a scikit-learn brief workflow, this is, recognizing digits out of, those of you who do neural networks will probably recognize this a bit. Even though it isn't using a neural network, it's using the kernel kitties approach. Okay, now trying to pull this all together, I will give credit to my colleague Ben Lorica, who's now at Gradient Flow. He had been for 10 years, leading a lot of the conferences at O'Reilly, helped create Strata and the AI conference. Now he's doing a lot of work at Gradient Flow. And Ben did an article along with Jan Strojka called Toward an Infinite Laptop to really explore the kind of architectural patterns that are coming out of Ray. And it really digs into what is RISELab talking about when they say serverless, because they don't exactly mean one-to-one what Amazon says with serverless. Their view is a bit broader. So I definitely recommend this article, Infinite Laptop. And in particular, there was a demo, just a jaw-dropping demo by Ed Oakes that landed at Ray Summit this last year. And I was teaching one of the tutorials at there, and I saw Edward's demo, and I was just like, seriously, I mean, totally upstage, right? I mean, I was trying to show cool things you could do with Ray, and this guy gets up there and just makes it do backflips. So check out that video. It really gives some idea of what's going on here. So this idea that, what if the word cluster meant a collection of hybrid and multi-cloud resources where, you and your team, your company, you're setting policies for what resources you have, you can use, you want to make the best out of it, and you're not necessarily beholden to one vendor. Some of the stuff is proprietary on your cluster because it has to be. Other stuff, you can move parts of the workload off to the cloud. How do you do that? And how do you do it within code that's easy to read and doesn't lead toward a lot of these sort of MPI-ish tech debt that I referenced earlier that so many of us had to live through. And that's what's really going on here with Ray. Okay, we're a little over an hour in. Let me go through this one section here about reinforcement learning and give you some ideas of, okay, taking these things and putting them into practice. I want to put some things in your hands where you can get direct hands-on experience with like some of the latest stuff on reinforcement learning. And so when we talk about AI with Ray, down at the lower level, we've got tasks and actors and remote objects and all the things, right? And there's ways to make PyTorch run ever so much faster by using Ray to speed it up. But then a level up above that, you start to get into abstractions used for machine learning. So in particular, I'm going to focus on reinforcement learning, and we'll dig into that a bit. But basically, Ray is providing this kind of control layer for distributing and optimizing the workloads across hybrid architectures. And it's really being mindful about the economics of computing, not just now, but like 5 years out, or at least trying to use the crystal ball from Berkeley. And this, pulls in a lot of other things. Is definitely working with Jim out of OpenAI and integrating a lot of others. What I've found over the past year being involved with RLlib is just other projects that already had momentum in reinforcement learning. They're showing up and saying, hey, we want to take our stuff and just move it into RLlib. How about? So Optuna and others were just like, yeah, we'd like to work with a bigger community. So let's just move our stuff into here. So a lot of that is happening. And this is kind of rapidly becoming an open source lingua franca for reinforcement learning. And I would say arguably, I mean, having worked some with other reinforcement learning systems, there's really good stuff coming out of OpenAI, but this stuff with RLib is, I think, much more approachable. There's definitely a community you can go to and get a lot more questions answered. At least for me, it was an easier learning curve. And same thing, I mean, there's great stuff coming out of like Salesforce research with reinforcement learning these days. But again, they're kind of in this mode of like roll your own reinforcement learning. So whenever I look at their GitHub repos, I sort of have to scratch my head and figure out like what? So I think there's a lot of benefit toward having, kind of a lingua franca and people building off of similar architectures. So reinforcement learning, I recognize, is something that kind of sounds like a buzzword. If we roll back, again, doing the connections thing, if we look at supervised learning, which is mostly what people think of when they're talking about machine learning, supervised learning is this idea that you have a bunch of historical data and you can use the past to predict the future. So you try to generalize from things that happened in the past that were recorded to be able to make predictions in the future. And we do this, most machine learning algorithms, you can be characterized in terms of a loss function and a regularization term, but you're trying to generalize from patterns, but avoid overfitting. And I won't dig into the math because that gets pretty gory, but that's the idea of it. Now, the kind of decisions that get made with these sort of crystal ball predictions, the contextual horizon for this is really down into the milliseconds. You're making judgments on the fly in an e-commerce website that's getting hit by millions of people per day. It's really fast. I had the opportunity last year, 2 years ago. I almost forget that 2020 happened. So 2019, I got to be co-chair for the Rev conference about data science leadership, and got to have Daniel Kahneman come for us and give the keynote. If you've ever read Thinking Fast and Slow, Daniel Kahneman is the Nobel Prize winning Nobel laureate behavioral economist who came up with the idea of that, co-authored that, about system one thinking and system two thinking. So this is system one thinking. And it's great for e-commerce. It solves a need, but it's really too shallow for the kind of complex longitudinal decisions that organizations, the judgments that people have to make about policy. And so supervised learning is sort of past predicts the future, real snap judgment. Reinforcement learning is a flip side, and this speaks more toward, again, if you're familiar with Daniel Kahneman, this speaks more toward the kind of systems two thinking out of Thinking Fast and Slow. And so reinforcement learning, you can go back through the decades. This really came out of optimal control theory. Back in the 50s, once people started traveling by air, and it wasn't just military pilots or postal service delivery. Once you really had a lot of people up in larger airframes, unfortunately during the 50s, there were horrible accidents where airframes would just start vibrating and like disintegrate and fall out of the sky. And so there was this huge effort to apply the latest and greatest in control theory and come up with better ways to manage complex systems. And so this idea of optimal control theory, full disclosure, I was at NASA years and years and years ago, and I landed in one of the branches that flight guidance and navigation, where like everybody there had a PhD in control theory. So I used to hear about this a lot, about how to make sure that planes don't fall out of the sky, but also how to really manage a busy air traffic control. And that was actually, I was working on the AI side of advanced air traffic control systems that if you've ever flown through Denver, you might have actually used some of my software. And I know that's kind of scary, but anyway. Optimal control theory has been around for decades, and it's used in so many places. The idea of reinforcement learning really is we can take and look at the edge cases and augment this by using deep learning to understand, once we hit an edge case and our system is starting to fall out of control, how can we vector back towards something that's better long term? Again, getting back to more of an optimal control operating kind of environment. The math for this is based off of Markov decision processes. And instead of trying to learn from the past and predict the future, instead what we're trying to do is learn policies so that we can guide an agent within an environment so that once things start to get out of kilter, how can we guide it back toward operating back within its normal range? And so the way that we do this is we have an environment, and we have one or more agents in that environment, and we have these feedback loops where the agent takes an action on the environment and then receives back a reward, a partial reward, immediately. And they also receive back a new observation about the environment. And then, the agent tries to do something smart, looks up its policy, and takes another action. So this is very different than supervised learning. It leads toward much more kind of long-term thinking and developing policy, which is really very different, but also very applicable in enterprise. One of the fascinating things about this is it leads toward maximizing cumulative rewards over time. And as a side effect, you get this thing called the exploration-exploitation trade-off. The agents can learn and adapt even while they're within a live environment. So over time, as the environment evolves, the agents can keep evolving too. And they can basically put together a budget for how much do they do that trade-off between exploring new things and weird things in their environment versus exploiting it as best as they can. And so that's very different because that's a kind of online learning that's not so common in the supervised learning. Okay, so you've got these feedback loops, and that's for reinforcement learning in general. Now, there's a policy that it's the outcome of the deep learning part of this is we end up with a policy. You can think of sort of like the deep learning equivalent of a big lookup table into millions and millions or billions and billions of edge cases. And then once you hit an edge case, what are the vectors back toward, getting into good operating again? And what's really fascinating about this is that the word environment is pretty much a plug-in for just about any kind of industrial simulations or any kind of industrial operations. And we're seeing this. There was really interesting talk by Dow Chemical at Ray Summit, where, I mean, this is exactly what they said. It's like, hey, we've got a bunch of chemical plants. I don't know if you noticed, but operating those is A, hard, B, valuable, and C, very dangerous. So, we like to keep things within control parameters so that chemical plants don't explode. People enjoy that. So, but what's really cool is we can, we've invested so much working with partners like IBM and others to develop really complex simulations over the years, CPLEX and all that kind of stuff. Now we can just come in with reinforcement learning and like drop it right in. And so you see companies like Pathmind that are doing exactly that out in industry. And they also presented about how shall I say, if I put this politely, a very large German automotive manufacturer that was very concerned about manufacturing automation on its floor. And so you get these really fascinating industry use cases coming out of reinforcement learning now. And I think that, one of the things is when I talk to the grad students who are working with reinforcement learning, they're not really into that much. They like this idea that they can simulate Atari games. That's cool. And it's like, no, actually really boring, but like extremely valuable industrial simulation. There's billions of dollars involved there. That's cool. So there's a little bit of an ageist thing going on there, I'm sure. Anyway, I think that we've got a lot of room forward in this area, and hopefully that can be helpful in some of your use cases. And sort of case in point, if you haven't seen it, this is really great. Stephen Zheng, and I hope I spelled his name right. I know I had a typo there earlier. Anyway, there's a really great team working on reinforcement learning. I got to work last month with Victoria Lin on a conference, who's also on a related team at Salesforce. They've been doing a lot. And one of the fascinating things was they took and did economic simulations about tax policies, trying to have AI-driven tax policies and just run them out over time as like these massive simulations. And they came up with this thing called AI Economist, which actually has some tax policies that, I mean, full disclosure, I'm a little bit more of a centrist in a lot of ways, and I'm not necessarily registered on either party. And I'm not going to get political, but the tax policies coming out of Salesforce that were like driven by real world data and using reinforcement learning actually kind of made sense to a person in business. And I think that there's maybe a long road ahead of like, can we actually use AI to come up with like good policy at a national level? I don't think it's going to happen tomorrow, but I think it may happen sometime. They were actually able to show that they were able to improve the trade-off between inequality in the tax bases versus improving productivity at the whole economy level by 16% over baseline policies. So they beat the politicians. Kind of interesting. Okay, having said that, let's dig into some examples that you can use. Here are 4 popular examples of environments that are used across a lot of different platforms for reinforcement learning. These have come out of studies over the decades. Some of these are actually pretty old. I did a series of a couple of articles for AnyScale that are up on Medium. One of them is called Intro to RLlib, and we do a compare and contrast of 4 different environments to show, what's the commonality when you're working with one of these reinforcement learning environments. What are you doing? What are the patterns? I'm a programmer. I understand patterns and I can use APIs. But what's going on? Because I came into this and I saw a bunch of different, code that had to do with somebody's PhD, and there's like differential equations, and nobody would explain what the parameters were that were being called. And I was just like, okay, that's crazy. Can I just get some design patterns and like, can you put this in front of somebody who's a software engineer? And so that's what I'm trying to do, is basically break it down. If you have experience in software engineering, better yet, if you have experience in data engineering, I hope this makes sense, because that's what we're trying to shoot toward. And there's notebooks for all of these. We really try to break it down step by step. What are the results you should see? What are the outcomes? How do you translate the graphs that are coming out? What does that really mean for the implications of learning that's happening in reinforcement learning? And then another article here is breaking it down. It's called Anatomy of a Custom Environment for RLlib. And the idea is that OpenAI created Gym, and everybody and their brother uses Gym. RLlib is from Ray. Gym and RLlib work together. That's one of the main ways you can use it. You don't have to, but it's a good way to use it. There are some nuances where they're not entirely compatible. And I kept running into problems where I would go and use somebody's code and then like, oh, sorry, that doesn't work in Ray. Or, oh, sorry, that doesn't work in Gym. So eventually I got really annoyed and started shouting with the equivalent of that on Slack, and just like saying, getting in front of the developers and saying, look, I want an example that runs consistently. And so we built this into a GitHub repo. It's basically a starter kit. If you want to go out and build a reinforcement learning environment for your use case, that's the intention. And admittedly, some of the use cases you have may be much more sophisticated than this and may need to use patterns that are much more advanced. But for starting out with reinforcement learning, what I'm just trying to do is like, this is the hello world. And it's something that wasn't there before. Okay, and also, kind of moving this forward, let's go and use these. So here's one of the components out of that we showed at Ray Summit that we did at ODSC and some others we've been showing. But this is a way of using what's called a contextual bandit. You probably may have run across the notion of a multi-arm bandit. Basically, if I take that feedback loop between agents and their environment and where they're getting actions and rewards and observations, if I simplify that feedback loop just a little bit so that the action that an agent takes on its environment doesn't necessarily change the environment, but it still gets an observation and a reward, and it still takes an action. If I do that simplification, number one, the computation is simpler, and so this is less expensive. And number two, yeah, that actually fits the use case. I mean, if I'm a trader in public markets, I go out and I, buy 100 shares of Apple. Well, I don't know if I can afford that, but I go out and buy 100 shares of Home Depot. That's not going to change the price of Home Depot. I'm not a big enough investor for that to happen. But I can still leverage observations as I see the market moving. And so that's the idea with contextual bandit is you have a somewhat relaxed condition, not full reinforcement learning, but for a lot of use cases, this actually fits better. And it's cool because there's some great optimizations mathematically that actually make this run much more efficiently. In this case, what we did was we took the US financial markets. I've got some data out of NYU looking at 9 decades, basically since just right before the market crash of the Great Depression up until, hey, the market crash of the 2020s. So we look at 9 decades of market data, and we look at stocks, bonds, corporate bonds, long-term, short-term bonds, and then we do some portfolio optimization, and to show how does that work inside of a contextual bandit in RLlib. And it's not that much code. It should be pretty easy to compute just on a laptop, and pretty easy to follow, what it's doing if you want to dig into the details. But, I also think that this is probably a pretty good starting point for other types of optimization that you might need. This definitely could be used in a lot of like online marketing, advertising, ad network kind of things, and other places where you have some sort of market that you're trying to optimize for. And then digging in a little bit deeper, here's a full-blown reinforcement learning application for a recommender system. And again, one of the things that this can do is, if you want, it can learn on the fly as the environment changes. What we did was we took a benchmark, a baseline out of the joke ratings database, out of the Jester recommender system benchmark out of Berkeley, and built a recommender system for jokes. And it shows some use of scikit-learn to do some of the clustering and analysis. But it's pretty straightforward in Python, building up a recommender system. And also, I mean, there's nothing sacred about jokes, really. For a lot of different types of item recommendation, user item recommendation systems, this code would apply. So if you're interested in using reinforcement learning for recommenders, this tries to take into account a little bit more than just your off-the-shelf thing. It's actually doing a warm start by doing some sampling, and yeah, there's a few nuances there to try to make it a little bit more like what you'd actually need in the real world if you happen to be responsible for a recommender system. Okay, and then I know okay, good. We've got time for questions, so I just want to show this last part real quick. This is a research project. It's what I'm working on. And here's why. If you haven't had a chance, this is Neil Thompson out of MIT. He's got a really great paper, but even better yet, he's boiled it down into a one-pager PDF, basically saying that we're hitting the point of decreased marginal returns with deep learning. And even though the cloud giants keep going after, I don't know if you saw the news, but now we have trillion parameter models for deep learning, even though the cloud giants are going after bigger and bigger models than custom hardware, this lab at MIT said, well, actually we're kind of underwater already, and we're seeing decreased marginal returns. You can keep building as big of models as you want, but we're not really getting close to goal. There's kind of a Zeno's paradox going on here. And the one pager that Neil Thompson did was brilliant. My colleague Ben Lorica did a podcast with him, really to kind of break it down. I mean, I love working with deep learning, but I also put on my cynical hat that it really is great about function approximation. But the flip side of that, it's kind of overfitting as an art form. And there are people a lot smarter than me, mathematicians like Mahoney out of Berkeley RISELab, who've really been going after just what is happening inside of deep learning in terms of the second order effects and Hessians and how the mathematicians really can't make sense of it just quite yet, which is more than a little bit disturbing. So that's one problem. And I will defer to one of my friend's bosses. Uli Sadler leads a department at UOM at Manchester. A couple of years ago, I got to go do a guest lecture there. Really great talk that Uli and I were both in the same track. We did lightning talks at the Semantic Web Conference this year. And Uli just did this jaw-dropping, brilliant 5 minutes here, talking about the need for leveraging both, really big machine learning models, but also leveraging domain expertise. And really the path forward for what Neil Thompson is pointing out, the path forward is we need to use both. And this is what we know out of a decade of data science is domain expertise is just so utterly valuable. I mean, you can have all the data you want, but really good, effective domain expertise will eclipse it. And so I love what Uli is saying here about being able to pull these back together. And reinforcement learning is one of the areas where this becomes a lot more reasonable, just given the available libraries and approaches that are out there today, particularly Ray. So this is a project that I'm involved on. It's called KG Lab. I may have mentioned earlier on working on graph-based data science. There's definitely a recognition of using a lot more connected data sets and graphs, whether you're talking about machine learning or just even data governance. But basically what we did was we've got a small team that's been building integrations out to a lot of different types of graph-based libraries. Whether you're talking about probabilistic inference, whether you're talking about GraphML, whether you're talking about semantic technologies, whether you're doing shackle rules or Sparkle queries, all these things, these camps don't usually talk with each other, unfortunately. So what we're trying to do is build an abstraction layer. We have been building an abstraction layer to make the different libraries talk with each other, but then on the one hand, make them speak fluent pandas, and on the other hand, speak fluent Parquet, so that you can take these workloads and integrate them with Spark, Ray, Rapids, but at the same time, be working with NetworkX and PyViz and PSL and things like that. And so this is an area, it's actually getting some traction. I did a PyData talk about this over the weekend, and I already had a couple of like industry use cases that are using the code and want to talk further. I think that graph databases are really useful, but one size fits all doesn't cut it. And this is really talking about more of the last mile of the machine learning side and other types of, again, hybrid AI, using rules-based approaches along with the machine learning. These are things that graph databases aren't going to do. And actually, I've got a podcast with DataStax tomorrow with their chief strategy officer talking about that topic. We're really looking forward to it. So long story short, what this allows us to do is, if you're familiar with doing graph-based work, the notion of a data object in a graph is something called a shape. So if you want to go out and, like Capgemini does, do compliance audits on very large graph data for instance, in Oslo, they have a project for, master mariners to get their license so they can pilot liquid natural gas petroleum, into Boston Harbor. You end up with a big graph and running shapes as rules. And so that gets into some interesting areas of like the sort of hybrid between machine learning models and rule-based systems, uses of graphs as tensors, abstract algebra, topology, etc. Long story short, what we've done is come up with a system where we can evolve shapes based off of the data that we see in the graph. And we put those shapes into a leaderboard based off of the things that we're trying to evolve toward. What are some of the properties? Like, do you have a rule that has coverage across explaining a lot of what you see in the graph? And the cool thing is that once you get evolved shapes on a leaderboard, now you've got, going back a few slides, something called a differentiable gradient, which means I can plug this into reinforcement learning and I can train a policy to go out and drive that evolution using reinforcement learning. And the business use case here is that we use this working toward being able to generate graph queries, generate validation constraints, axioms, inferred relations that we can use for really complex audits, but also inference across the graph. Like, we can start to point out places where we think you've got a data quality problem, and not just in a vague sense, but like, out of 1 million elements, here's the 150 that somebody needs to go look at like yesterday. The other cool part about this is that the libraries, some of this stuff was, they started building this stuff back in the 90s. And so a lot of these libraries are sort of built thinking that XML was a really good idea. And so they need an update. And it turns out that the stuff that's right at the core of parallelizing it is just ripe for working with Ray. And so that's one of the projects that's going on, and I'm grateful for some of the people that I have partnering on that. And we can go and talk about that more, but just pulling it all together, the AI workloads that we have today, they really, as Jeff Dean said, 8 years ago, They require much more complex graphs. And as Uli Sadler is saying, we leverage the machine learning models with domain expertise. We know this. And it's taken decades to get to this point without having some vendor saying, no, 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 we're going to do that for you. It's taken decades to actually have good libraries that can do this kind of thing. Because there's a lot of balkanized code out there when it comes to graph-based approaches. And it turns out that the advanced math and the functional programming and distributed systems all kind of come together here. And we're trying to move away from this like 1960s notion of just make it a matrix, because actually we do have to be worried about things like GDPR and explainable AI and all that. We're accountable. So that's what's going on. And I will point you toward Ray Summit coming up on June. The CFP is open. We'd love to hear your talks proposed. There's a little bit of a splash page about it. Signups will be coming up, forthcoming, but the CFP is definitely open, and mark your calendars. And also some other items of interest recently. If you haven't caught them, I thought they might be good for you. I got to host something back in October called the AutoML Summit, and we really had some fantastic people out of H2O and Determined AI and IBM and others who are doing really crazy, amazing things in AutoML that you could put into practice like tomorrow. So the videos are all online for that. Ben Lorick and I did a survey of NLP use cases in industry. We came out with some pretty surprising results. That is up and available. I've done a couple talks about it. The KG Lab thing that I've done, I've been doing some workshops, again, for enterprise people to be able to have really convenient tools to work with knowledge graph and different graph-based techniques. I actually just got off the phone with my colleague, Shashanka Das, who led a lot of the GDPR effort at LinkedIn, one of Joe Hellerstein's grad students. But we did an event called Metadata Day. If you haven't heard about it, go check the videos. Every enterprise shop that I've run into, they're like, thank you. Metadata Day was this realization by Netflix, LinkedIn, Uber, Airbnb, Lyft, etc., that, oh, wow, GDPR, that's a pain. But then they started pulling together the metadata, but also the operational data that they had for usage of data sets. And they realized that once they got that sort of 360 view of their data set usage in place, they're like, oh, wow, we could open up entire new business lines. And like Lyft, the case study from Lyft, they immediately found 30% 30% rise, 30% lift, no pun intended, on their entire data science team, which for them happens to be about a $20 million a year spend. So no small potatoes. So check out Metadata Day. It's about these practices, graph-based practices from the tech majors, but then as they're filtering out into enterprise, what you can do to turn compliance into business upside. And there's also a really great talk, a seminar series, Responsible AI in Practice recently. And Ben and I do surveys. We've got one right now in progress, the AI in Healthcare survey, and we'll be doing the NLP Summit about healthcare based on that survey and doing a report about that coming up in April. And I think that's all I've got. I'll turn the time over, Doug, and love to go into some questions.
That was awesome. Thank you, Paco. I mean,
thank you.
That was awesome. Let's have a little chat clap here since everyone else's sound is turned off. But that was awesome, man. That was like Paco Con.
Yeah, thank you. Feel
free to trademark that.
Yeah.
So excellent. I see them coming in right now. So do we have any questions for Paco? Here we go. Okay, we got you mentioned the rapid rate from question from Mark. Rapid rate of change in hardware. Are these changes in computing architecture or more incremental changes using familiar architectures? Can you provide some examples of recent advances?
Certainly, yes. So, I mean, there are some pretty mind-boggling things coming out of the architecture, like what's going on in ASICs, but also FPGAs, interestingly enough, and some other areas. But I don't mean to be too much of a hardware geek. I used to work in hardware, and I used to be sort of like the software person in hardware teams that they would kick around. But one of the fundamental problems with like hardware accelerators on neural networks is, we had the 300-watt thing where basically we could build large chips to do phenomenal things with deep learning, except that almost certainly they would melt. And so for a few years there, everybody was struggling with this like fundamental limit in physics of like, yeah, we can build it for you, but it's going to melt. And finally, Cerebrus, I don't know if you've seen Cerebrus, but they have this like wafer scale thing that's like, several orders of magnitude performance increase. And, some of the, like DoD and others have been buying them. They're very expensive. I got to hold one of those wafers backstage. One of the co-founders came out and did a talk. So there's some really crazy stuff going on in the ASIC world, but there's also some really interesting stuff in the definitely the FPGA and sort of what's a little bit more mutable than a wafer scale ASIC. And there's also a lot going on in the TinyML world, which I think is really fascinating out on the edge, super low power stuff with it, where you have like, you can run neural networks, deep learning on bare metal, no operating system, with the power requirements that they can run off of ambient light. Really crazy stuff. So yeah, there's some fundamental things down there in terms of how you build hardware that is certainly nothing like a CPU, or as we know it. An operating system, more importantly, on top of the CPU. But I think what's also going on, there's this fundamental shift that we're tracking out of, like I say, some of my colleagues in NVIDIA, where there are ideas that just avoid the hardware because really the software is this abstraction layer. You don't need to worry about it. And it's like, no, actually, there might be something where there's a 20x cost by using GPUs, but you get a 100x return in performance. And when you talk with people, they're like, oh no, we can't use GPUs, it's too expensive. And I'm like, you're running that workflow all day, every day, and you're basically paying 5 times too much for it. Just, can we do the math? And then like, yeah, but the code, God, CUDA. And it's like, no, it's 2 lines of Python. So, I mean, I think that there are some real fundamental things in terms of how do we approach workflows. And unfortunately, I mean, I'll be one of the first to say, even working with NVIDIA and friends over there, some of their documentation is really awful. I mean, I've been around software engineering for decades, and I read some of that stuff, and I was ready to run screaming in the opposite direction. So there's kind of a communication problem, I think, of like talking with people about how the changes in hardware have a lot of impact on operating systems. What's going on with like Apache Arrow is another good case for like large memory spaces. And how much that really fundamentally changes things. And it does go back to what Eric Jonas and others were talking about in that paper out of Berkeley. And so just showing people examples of like, we can make your workflow twist it a little bit and do backflips. I think that's a lot of what we'll see. I hope that that starts to answer the question some. And yeah, I'd love to see memristors, but no, that's not really part of it.
Oh,
Cool.
a little comment says, yes, it did. Thank you for that answered his question. Question from Abby, what developments in machine learning are you most excited to see or hopefully see in the future?
Oh, very cool. Very great question. I when I was like just starting out as a student in AI and kind of hanging around people like Niels Nilsson and whatnot, and like trying to listen to them and not, annoy anybody. They were talking about some pretty cool stuff, and they could definitely show like proof of concept, but they didn't have the hardware. And I've got to be honest, the machine learning parts of it really were like minuscule part of it. They were talking about big ideas about planning systems and scheduling systems and the hard AI problems that really do take intelligence. And there's probably no coincidence that okay, so full disclosure, my graduate advisor back at Stanford was one of the early people in machine learning, and he had been at Carnegie Mellon and Stanford, and he had done work on machine intelligence, and he got a lot of flack because people are like, oh, well, this is just empirical. I mean, all you're doing is taking a bunch of data and training up this software, and it does fantastic things, and you call that machine learning. Ha ha ha. And so he didn't make tenure at Stanford. They booted him. And the irony is that some of the professors, at least one of the professors who was on that committee, who turned down Doug and said, your stuff is too empirical. A decade later, one of those guys had written out, $100,000 check to a couple of founders for a little company called Google. And so literally a decade later, the same guy that was saying machine learning is not academic enough was a billionaire because of Google. And I mean, okay, Doug's a little bitter about that. I'm a little bitter about that. But realistically, there was a lot of cool stuff that people were working on that didn't have a lot to do with machine learning algorithms back then. And so I would go back to like, this project that we're doing with like graph-based reinforcement learning. And what I see like Victoria Lin and others at Salesforce in similar areas, I think it has a lot of bearing, especially on natural language. And it cuts to the chase of like really hard problems in natural language that unfortunately right now, most of the industry is saying, we'll just make a bigger model. And it's like, okay, but your model has a carbon footprint of like 5 Volkswagens run over their entire lifetime. And I can beat that by incorporating rule-based systems that have, auditable trail of human expert domain expertise. And it has a much smaller carbon footprint, by the way, and a much smaller price tag. So I'm really fascinated to see what's coming out as AI moves beyond sort of this hegemony of Google. No offense, I've got friends there, but I think we've just really over-indexed on this idea that some smart people who happen to own a cloud can build really ginormous models. And it's like, that's kind of a one-trick pony. And I think the real thing is that like out in the field in enterprise, you have a lot of people who know their business and they do stuff that's real, like, hardware for cancer treatment or like insurance companies. I, for one, happen to like having insurance. And so I think that in the real world, there's a lot of real world problems and they beg a lot of domain expertise and it's not going to come out of Mountain View. So I'm number one, I'm kind of grateful for, bright side of the pandemic is, I left Silicon Valley 5 years ago and I've just seen people fleeing. And I hope that they move off someplace else and that more of the thought leadership goes out into the field and in the enterprise and into like actual real business. And with it, picking up a lot more of these kind of hybrid techniques of like, how can we make the best out of, human expertise, but also human in the loop? And yeah, we'll use really interesting machine learning and reinforcement learning and weak supervision and some of these areas that are kind of newer. Some of the self-supervision is pretty interesting, but let's put the people in the equation too, because we absolutely must have that. Does that?
Thank you. So we next question is from Ethan. Are there any promising democratization efforts for machine learning model implementations as model size and training grow beyond the hardware capabilities of individual developers and universities?
Yeah, that's a great question. There's a lot to be said about transfer learning, and I will paraphrase somebody who can say this much better than me in terms of like Lucas Beowald, who founder for Weights and Biases, got to work with him about 11 years ago on something. Realistically, the big tech majors go out and train these big models off of big data sets, and then we start to use tricks like transfer learning to adapt them. And I know that DARPA had sort of a small data challenge and put about $3 billion toward that. And we see like zero-shot training and others. So we're definitely seeing a lot of mindfulness toward, hey, we're not Google, we're not Microsoft, we're not Amazon. We have a real problem. We don't have mountains of data. We'd like to reuse something else as a starting point. So you do see more of these kind of democratization efforts. But I think I would take big exception, and I know I'm going to get in trouble with it, but like people like Jan LeCun are running around at Facebook saying everything is deep learning. And I don't believe that. And so I think we need to get past that. And that'll be a lot of the key to the democratization of it. And I can see that I already got in trouble about being flippant about memristors. Hey, and I love this idea. And actually, I worked on a hardware project that was really strange back in the 90s. Some of my friends in Austin who were actually trying to commercialize something like that. And I do think that there's way forward on this. So I don't mean to dump on memristors. I was actually kind of saying that affectionately, but I do think that realistically, the things that are changing in hardware have a lot more to do with switch fabric and large memory spaces that has a lot more impact, multi-core and GPUs. I mean, you know, I was back in Kansas City in 2008, where, you know, we got to do that work with like the first large scale Hadoop cluster on EC2. And I took that data a few years ago. I took the data rate, I took the algorithm, and I rewrote it from Java. I rewrote it in Python, and it ran it on my laptop faster than like what at the time was like the reference implementation for a large scale Hadoop cluster on EC2 using really expensive, and it ran faster in Python on my laptop. So I mean, I just want to say that like multi-core and memory spaces have made a big change, and you may not really need a whole lot of cluster compute in a lot of cases. And so you want to be careful about that, because I have seen case studies of where people are like, let's go parallelize this. And then they're like, crap, it runs 3 times slower. And so I think that the world ahead, I think the big things that are changing kind of, again, goes back to like what Eric Jonas out of Chicago was saying. You know, we're going to see a lot more of a sort of serverless world if we can take the definition of serverless and make it a bit broader. And you're going to see a lot more of hybrid cloud, multi-cloud, making the best out of multiple vendors. I think that's what's really changing underfoot. I hope that answers the question.
That's awesome. Thank you. One thing to add, I did a talk like 5 years ago where it was kind of a response to a lot of the narrow definitions of big data that were kind of annoying me, of like big data is the 4 V's or the 5 C's, or there was, you know what I'm talking about? Like I don't remember, it was, but people were trying to define it really, really narrowly. And I did this talk a couple of times. I said, can you run it on a laptop? No.
Yeah.
And you have a big data problem. You
Exactly.
have to involve, like, as far as you're concerned, you have a big data problem because you have to involve multiple machines, either to store it or process it or to do whatever you need to do. But defining it in absolute terms is kind of pointless.
Yeah, no, that's so important, so helpful, and thank you for doing that. And we need to see more of it. I mean, I got the feeling for a while there that you could just sort of make something up. It's like, it's about the 11 Z's or the 12 X's, and people would nod their heads and go, "Oh yes, I've read that." And you're like, "No, you haven't." Yeah, no, it got pretty weird there. And case in point, when my team got pulled into Kansas City so many years ago to work on that Hadoop cluster, the problem was they had an Netezza cluster that was failing. They had like a job. It was an advertising company, and almost all the revenue went through this one job. And it took about 11 hours to complete. And the problem was the job was failing in like hour 9, but nobody would find out about it for about an hour, which meant that they would be working with stale data the next day, and they'd lose, you know, lots of money. And so, but the punchline was they had brought somebody in and managed to chase this person away, the person who had created the machine learning algorithm. And so they had this whole Netezza cluster, which was failing. But the very last part of it literally was running on somebody's laptop. And so the machine learning part only ran on the laptop because they had managed to, how should we say, not be good citizens, and had deeply offended somebody that they'd hired who had left. And the only artifact they had was this individual's laptop. So they just kept running it in production. And eventually they realized, wow, we're gonna have to scale beyond this laptop, because like the entire company, which at that point had taken a $150 million B round, was dependent on this one laptop, which wasn't even in source code control. So yeah, I love what you're saying, because I have lived that nightmare.
Oh my God, that's awesome. I mean, not awesome. Like it's funny, awesome, but not to live.
That was crazy.
Let's see. Do we have one last any other last questions here? So I got a thank you from Ethan, said he answered his questions. Thank you from Abby, says that answered her question.
Thank you very much.
Let's see. We got the Memristor question.
Thank you, Connie.
Yeah, a bunch of thanks coming in here. Looks like we're it for the questions. Again, Paco, thank you so much, and thanks for everybody for attending. Yeah, just that was fantastic.
Thank you all. I really enjoyed the questions. I look forward to a day when we can all get together, and I hope to come and share some pizza and beer with you.
Awesome. Look forward to it. Thank you, Paco. Thanks for everybody for sticking it out. This was fantastic. Thank you.
Hey,
Thanks, John.
everybody. By the way, thank you, Doug. Thank you, John. I really appreciate it. Thank you, Linux Foundation. And please, everybody here, if you have any questions, please reach out. I'm all over Twitter and, connect up on LinkedIn. I'm also doing office hours, public office hours once a month through the Knowledge Graph Conference. And we have an open Slack. And, we put those on our event calendar. And I may also start doing open office hours monthly out of Anyscale. So if you have questions, I try to be involved very much in different open source projects, but I also just really love talking about use cases and all. So yeah, cool. If I'm Pacoid on Twitter, and then KGC conference. If you hit me up there, I can guide you more toward everything on that. Also, let me one more time. My slides are right here. Just so you see it, a lot of the links are here within the slides. There's a lot of primary sources and a lot of other kind of materials there too. So all that info, if you hit me up there, that's probably the best way.
Awesome. Good stuff. Thanks, everybody.
Have a great evening.
Thanks. Bye.
Okay, bye.